Section 2.3, polynomial regression. Up until this point, we've done very simple data that's been able to be described by a linear line, right? And then this is where we tell you that all of machine learning is just curve fitting. Most of it's built on, or at least can be built on, least squares estimators and gradient descent. But what if we have a data set that's more complicated than what we've seen so far? So we have this data set where we have X and Y, and there seems to be some sort of complex shape, right? Now, if I were to just draw a straight line through this, I wouldn't be able to make a very good approximation. So what I actually want to do is draw some sort of curve that looks like that, right? So let's say I can model this. Let's say I pick a model, and that model I'm going to pick is y hat equals a to the x squared plus bx plus c. So I pick a standard polynomial model, and that's what I want to use. So how do I fit that data, kind of using the tools that we have, and how do I train the model to actually get there? So to do that, we are going to do polynomial regression. And polynomial regression is quite interesting, that we're just going to break the data up into its more constituent parts. We're going to fit a linear regressor through each of those constituent parts, and then we're going to rebuild it, right? And it's really interesting to think about, because it helps you to think about how you get to play around with data and how you get to extrapolate and kind of, I don't want to say misuse data, but how you get to use data in more of a data science approach to get the answer to be able to fit some complicated models. So in polynomial regression, all we're going to do is take our data, and that's here x, and I'm going to fit a line through my data, right? And then I'm going to take x squared, and that's what I have here. I just have the same data, but I've squared it, right? And if you square the data, it's always going to be positive. So I've really flipped it around my axes, and now I'm going to fit a line. And so now if we think about this, let's take the blue, let's do red. So let's take this red line here, and that's going to become this parameter b. And then I can take this green line here, I'm just picking different colors to make it visible, and that's going to be my parameter a. Now the goal is to go ahead and find the solutions. So a couple things to note here. It's important to note that the polynomial regression can identify the interrelationships between features, and multiple scaling features exist, right? But it scales quite poorly, right? So here we've got x and x squared, but if we wanted to do degree 3, so for degree 3, we would have to do a squared, a cubed, b squared, b cubed, right? And then we would have to combine all of those. So we would also have to do ab, a squared b, and ab squared, right? Polynomial regression, super interesting to look at when we're looking at kind of things that we can model as simple polynomials, but as things get more complicated, it gets very expensive. And that expense comes with a cost. Doesn't mean it's bad, but it does get expensive. So we can mathematically kind of write that out a bit. So if we look at the scikit-learn, the scikit-learn code or function called polynomial features. And that's degree equals D. That expands an array with n original features to n plus D factorial divided by D factorial n factorial, accounting for all the combinations of a D degree, right? So remember here that n factorial represents the factorial of n, right? So that's going to be 1 times 2 times 3 times 4, times n. So that gets quite big. So if you're trying to do a fourth order model, a sixth order model, it can get quite expensive. If your computer is big enough, it's not the end of the world, but it's definitely not an absolute freebie.